All right, so as I was just saying, our final will be Wednesday from 1 to 3. And I'm going to change rooms because of the construction noise. So that'll be in North Santiam Hall 110. Okay. So North Santiam Hall 110. All right, now there's one last thing we want to do with pumps here. We want to look at curves, because when you get a pump, you get a pump curve with it, okay? And what this curve does is describe how the pump will act. Now, there are a lot of different variations on pumps and how they run, but a basic pump, the key thing to understand about it perhaps is that it doesn't have a throttle, okay? It's like kind of like if your car just didn't have an accelerator, if it was always just pushed down to the metal, okay? And that's how pumps run. Now you can change that with fancy controls. You can put variable speed and variable frequency drives on pumps, which is getting, I think, more common. But if you don't have that, the pump just does what it does. You don't control it. It just runs, okay? So what you need to do is, before you buy a pump and install it, is figure out what your conditions are going to be for your piping system and how high you have to lift the water and what the piping system is and what flow you want, and then pick a pump that will do that. So you figure out what your conditions are, then pick a pump that will perform in the way you want it to perform, okay? That's generally how this goes. So let's have a look here at a pump curve, and this is on 147. There's a lot of information on pump curves. The way it's presented is usually pretty standard, but they can vary a little bit in the details of how they're shown. So the basic line is this line right here. Okay? So what you have for a pump curve is you have the head that it develops on the left and the flow rate. And the line that I just outlined there in dark blue tells you how the pump will operate. So basically, with a pump, what you have is a trade-off between the head, which is the pressure you develop, and the flow rate. So as you generate more flow, you have less pressure, okay? So you've got a trade-off between those two things. And there's always a line on a pump curve that shows that relationship. So what's going on with this pump here is, if you're going to have a flow of 800 gallons per minute, you'll develop 160 feet of head, which, if you want to know what pressure that is, just multiply by 0.433, and that would tell you the pressure. If you want to generate 2,400 gallons per minute, you're going to generate a lot less head when you do that, okay? So you can't have both of them. You kind of trade off between the two. That's the idea. Now, there's other lines on a pump curve also. Quite often there's efficiency lines, because you're concerned about what your efficiency is going to be, because of course that affects the energy you need to buy. So the efficiency lines are shown in different ways. Quite often they're shown as bands kind of running through the pump curve. So what we have here is just a series of efficiency lines. So you can get as high as 90% with this, and as low as 20%. It just depends what you're running. So obviously, even though this pump would do it, I would not want to pump 200 gallons per minute at 180 feet ahead. This pump will do it, but the efficiency is down around 20%, so I'm not going to want to do that, okay? So that's kind of what you consider when you look at a pump. The other line or information that you have on a pump curve is something that tells you what the brake horsepower is. Remember, the brake horsepower comes out of the motor and it goes to the pump. So this is that horsepower that comes into the pump. So this is what the pump's going to consume. It's also how you would size the motor, okay? Because you size a motor on what it puts out, what comes out of the motor. All right. So those are the common information you've got on a pump curve. All right, so if you've got 800 gallons per minute, let's say I know I want to pump 800 gallons per minute. Let's find out about this pump. What's it going to do if it's pumping 800 gallons per minute? Okay. You just identify your flow and just go straight up. And then you can start reading information about it, okay? So if we're pumping 800 gallons per minute, how many feet ahead do we got? About 160 feet. Now, if by any chance you want to know what pressure that would be, because normally if I imagine a lot of you have been around pumps, you've probably, looked at the gauges and stuff. There's a pressure gauge on a pump usually, right? I mean, it's telling you the pressure it's developing. So what that would be equivalent to on your pressure gauge would be about 69 PSI, okay? And it's just a simple conversion as we've done many times, okay? So that'd be about 69 PSI, thereabouts. Okay, brake horsepower. Now, the way this pump curve is set up is there's a brake horsepower numbers over on this side. So what? So if we intersect here, we'd read over this away. And that looks to be about 50 brake horsepower. Okay, so that's what that pump's going to need input to do this. And then you want to look at the efficiency. Now the efficiency is found on this pump curve right there where the intersection is with the TDH line, the headline there, the operating line. It looks to be between 60 and 70%. This is one of those things where we don't get too excited about it. I'd guess that's about 64%, something like that. Okay. So 63, 64. So we okay with that? That's basically how you read those. Okay, now let's see if, now let's just run a quick set of numbers, just because see this stuff isn't just stuff on a graph. It should relate to what we've learned. So let's find the water horsepower here for this thing. So what would that be? That would be 160 feet times 800 gallons per minute, right? And then you divide it by the conversion, 3960. And let's see what the water horsepower would be. So 160 times 800 divided by 3960. About 32.3. All right with that? So that's the power that's going to go to the water. And then let's find the efficiency of the pump, because what it's going to put out is 32.3 horsepower. And according to our graph here, what's coming in is about 50 horsepower. So when we divide that out, what do we get? Okay, 64.6 is what I'm getting. You all with me there, what I'm doing? And see that, Matt, that's about right. I didn't read that exactly. I called it 63 or 64, Okay, so that's how this stuff all fits together. It's just a graphical representation of a lot of these calculations that we've learned how to do already. Okay, it's all just put on a graph. You okay with that? Okay. All right, so that's basically how you read these things. Now, we did some TDH examples already, and we calculated some stuff. Let's see how this pump would work for those situations. We did a static head example, and that is when we were doing the TDH. And I think that was the one on page, let's see. What did I call that? Okay, this is the one on page 140. I didn't label that properly. That should be the static lift example. All right. So let's say we have that piping system that I'm showing on page 140, and we ran through the numbers on that, and we came up with a TDH of 139.4 feet and a flow of 1,300 gallons per minute. Now let's have a look at this pump. Let's plot that up on this on this pump curve, and let's see how that fits, okay? So is that about 1,300 gallons per minute? Right about there, and 139.4 feet. So right about there. Okay, you all with me? Now, see that analysis on page 140, that wasn't done for a pump. That was done for a piping system and a flow rate through that piping system is what that was done for. On page 140, what we had this, we said, okay, we're going to pump 1,300 gallons per minute through that pumping system, that piping system. How much TDH are we going to, will there be? And it comes out to be 139.4 for 1,300 gallons per minute. Is that a decent fit on our pump curve?
It's pretty good,
Yeah, that's not bad. How about the efficiency?
It's pretty good.
Yeah, you're not going to complain about 85%, okay, generally? Okay, so this, if I had that piping system on page 140, this would be a good pump to pick, okay? It would fit. It's on the operating curve, and it's got a good efficiency range, okay? So I did a pump design a long time ago, and I had these curves on computer, and I calculated the head and did all that, and put that in, and then it pulled up curves and matched, which pumps from this vendor would be a good fit. That's kind of how that worked. Okay. And again, I want to emphasize to you, it's not like pumps have a throttle on them. They don't have a gas pedal. You just put them in and they go. Now they can have a gas pedal if they have variable speed drive or something like that. But generally speaking, a simple pump doesn't. You just plug it in and it goes. So you got to pick one that'll do the job you want. And that's kind of what we were talking about earlier. Sometimes the job you want might change a little bit. So you might have to start messing with your pump a little bit to change it. Okay. All right. Now how about the one on the previous page? Okay, same flow rate, but on that one, yeah, and I didn't do a good job with this labeling here. It's a static head is what this one was, so I didn't label this properly. Okay, so this is on page 139. All right, what's going to happen for this one? Okay, we want to pump 1,300 gallons per minute, and in that condition there, in that situation, we found out that our TDH, I think I screwed up, it's 50.8, isn't it, on page 139? Mm-hmm. So I got all sorts of typos here, yeah. 50.8, okay. 50.8, okay. Well, that's down here, isn't it? See, that doesn't fit, okay? This is like, giving your 16-year-old a Harley for their birthday, okay? It's way oversized. You don't want to start with this, okay? This pump just isn't made to do this, okay? And so what's going to happen when that pump starts to pump and it hits 1,300 gallons per minute, and when it does that, it encounters 50.7, 50.8 feet of resistance. What's it going to do? Okay. It'll be like that time I had a line drive and when I was playing softball and the third base coach tried to hold me up, right? And I said, I don't think so. I don't have too many chances for a home run in this game. I'm going, man. I'm going. All right, so that pump's going to go that way, okay? It's just going to pump more flow, see, because it hasn't reached enough resistance yet. So what it's going to do, it's going to push more flow and it's going to slide into home base. It's going to be safe. It's going to have a home run. It's going to be pretty good. So what's going to happen there? See, that thing's going to shoot further out. Okay, and it doesn't just stop here because the pump doesn't run there. It's going to keep pumping more flow. When it does that, it's going to get more head loss, and it's eventually going to keep doing that till it hits the pump curve out there over to the right. And my guess is by the time it does that, that efficiency is going to be down pretty low. This is not the pump for the job we want to do. It's going to push too much flow, and it's not going to do it very efficiently. This pump is way oversized for the job we want, or excuse me, yeah, for this particular job, it's oversized, okay? You okay with that? And so the moral of the story is you just can't get any old pump and plug it in and expect it to do what you want. You've got to pick a pump that will do what you expect, what you want it to do, okay? And you can work with pump vendors on that. they're happy to sell you a pump and sell you the right pump, I'm sure. Okay. All right. So that's just a little bit on that, okay? Now let's skip ahead a little bit and let's just look at pump curves a little bit more, some more detailed ones, okay? There's a little bit there on operating points, but I think we'll skip that for now. We'll come back. So let's look at 151, advanced pump curves. Okay. So what I have in there are some real pump curves. That one I showed you is one that's just kind of drawn from scratch, a little simplified. Let's look at a couple ones that you'd actually get, and they're on page 152 and 153. Let's have a look at those. So the first one's on page 152, and that didn't copy very well, so I wrote some stuff in there by hand. Now this is an industry level pump, okay? And the way this thing works is, so you can buy a pump and put 4 different impellers in it. The impellers have different sizes, and they're over there on the upper left. So the biggest impeller you can get is 7 3/4 inch diameter, and the smallest is 6 7/8. So they put all 4 of those on the curve. So this is actually 4 pump curves, is what it is. Okay? That's one thing to know about this. The second thing to know about it is you adjust. This is also set up to be a multi-stage pump. Okay, which means it could have more than one volute on it. If that's the case, you can put on 1, 2, or 3 volutes, which they call bowls, because it's like a volute bowl, and you have to adjust the efficiency depending on how many bowls you've got. Okay. All right. They give you some information about the bowl diameter. They got the RPM, 1460 RPM there, down on the right-hand side. And they also give you the brake horsepower for each of those impellers. Okay. But the basic setup on the thing is pretty much the same. We've got gallons per minute, and then we've got TDH on the y-axis. So that's a pump that's set up for more than one impeller, and 2 has it's set up to be a multi-stage pump too. All right. All right. And then we got 4 lines for impellers, 4 lines for brake horsepower. So let's have a look at this one. Okay, let's start off. Let's find the TDH, brake horsepower, and efficiency for a single stage pump with a flow of 300 gallons per minute and a 7 3/8 impeller. And what do you have in your book? Why don't we match what you've got in your book? And I'm sorry about this. I think I have a little disconnect between the two. Page 151 is where I'm at. We're going to start with let's see. Why don't we start off at the next pump? I'm sorry about this. I just want to kind of match what you've got. So let's do that. Let's start with what's called the hydronics pump. Okay, it's this one, 7 3/4 impeller. So this one has 5 different impellers. Okay, it's on the next page after the jacuzzi pump. So what page is this? 153? Yeah. 153. Okay, let's start with this. And then I've got a question there on page 151. And I have an older edition of the book, so let's be sure that what you have matches what I have. So for the hydronics pump curve with a 7 3/4 impeller, find the flow rate, brake horsepower, efficiency, and required NPSH when pumping against a head of 40 feet. Yep. Okay. Let's do that. Let's have a look at that. So in this one, we're pumping against a head now of 40 feet. Okay. So let's find the head here in feet. and we're using the 7 3/4 impeller right there. So what I would do then would be to extend out, because I know I'm pumping against 40 feet of TDH, and just keep going until I hit that curve line. You all with me there? So I'm just extending out horizontally from 40 feet, and I'm looking for the TDH line. Now what I'm looking for is where those two things intersect. Okay, so that's where that pump with a 7 3/4 inch impeller diameter, that's where that's going to operate when it's pushing against 40 feet ahead. Okay. Now what we're going to do then is drop vertically down from there and then start reading some things. Okay. So we'll come on down. All right, so what kind of flow do we have on that?
400 GPM.
Yeah, 400. I got just a little bit. 400? Okay, we'll just call it 400. Is that good? I got about 425. I mean, again, it's kind of like head loss. We're not going to, argue about a small change. So we'll call it 400 gallons per minute. All right. Now, how about the efficiency? Now, we're right about here. These efficiency lines are running through there and there. They're curves that kind of run through. Which efficiency lines are we between right now? 58 and 60. So efficiency is often shown with a backwards 3. That's a Greek letter epsilon is what that is. It means efficiency. %, near enough. Okay. Now let's find the horsepower here. We're right here. Now this is a little bit funny how this one works. This one has the horsepower lines running here. What they're doing, they're recommending motor sizes. See, is what they're doing there. So about what horsepower are we at?
8.5, 9?
No, I think we're down pretty close to, yeah, 7.5.
Yeah.
So what that means is that these are the motors that are probably available for this thing. It's kind of how I'm reading that. So you're probably going to go with a 7.5 inch. So you're getting 7 to 7.5 brake horsepower. And see, that's how you rate your motor. So my guess is you'd pick the 7.5 horsepower motor. Now, if you're somewhere between 7.5 and 10, you'd round up to a 10 horse motor, but you wouldn't round up to a 15. You don't want to oversize the motor. You want to pick the motor that matches. So, so on this one, I think the 7.5 horsepower motor would be the one to go with. We're at about 7 brake horsepower. All right, now the other thing on this pump curve is there's NPSH. So what you can do is you can read this over sideways. And here's the NPSH that you are required to have. Yeah, I'd say about 12. So you could run those NPSH numbers and say, I'm going to have at least 12 feet of energy in the volute. If I don't, this pump won't run properly. Okay, that's what that means. Okay, so that's 12 feet. All right. So we all right with that? We're good. All right. So that's that pump curve right there. Notice this thing is a self-priming pump. Maximum solids 3-inch diameter, so that appears to me to be a sewage pump. So an open impeller, and notice the effects that has on the efficiencies. On the other one, we were looking at 80 or 90% efficiency. On this one, we're looking at 50 or 60. Okay, so that open impeller, that it won't clog as much. But the efficiency, you pay for that with efficiency. Looking at 1750 RPM. Okay. So we good with that? Okay. All right, now let's have a look at the jacuzzi pump now. Okay, now Jacuzzi does more than hot tubs. You know, they do serious industrial pumps and all that. That's a big part of their business. So let's have a look at this one now, and let's look at the second question there. Find the flow rate, efficiency, and brake horsepower from a single stage pump using a 7 3/4 inch impeller, TDH of 25 feet. The 7 3/4 impeller is the top curve. Okay. Read that over this way till you hit the top curve and then read it down. Be the thing. I think anyway, yeah, I'm hitting that about right. Is that what yours says? It says 7 3/4 impeller, TDH of 25? Right. So about what flow do we have there?
About 80.
Yeah, 480 gallons per minute, okay. How about, we good? Efficiency? What's the efficiency going to be?
Seventy-six.
75 or 6, either one, you know, again, let's just say 76, but pay attention to these notes. What, we got a single, how many bowls do we got? We got a single stage pump. What is that? How many bowls is that?
4.
No. Single stage, a bowl is a volute. It's a stage, yeah. 1. So what do we do to the efficiency? Drop it, yeah. Drop it by 4, okay. So 72%. Okay. You okay with that? And then the last thing here, we're going up, we hit that line. That's the brake horsepower line. Now notice there's 4 impellers. There's 4 brake horsepower lines. They match, okay? So we go up till we hit the top brake horsepower line, then we take it on over. There's our horsepower, our brake horsepower, okay? So you got to pick the brake horsepower line that matches the impeller line that you're on. And so that comes out to be 4 brake horsepower. So, we all right with that? We pick the one that, see, there's 4 brake horsepower lines, and there's also 4 impeller lines. We're using the top impeller line, so we use the top brake horsepower line. That's good.
Oh.
We all right with that? Okay. Now let's look at, if we're good with that, let's look at a little trickier one here. And it's the third question on 151, and I kind of made some edits to this. So it should say for the jacuzzi pump, find the flow rate, efficiency, and brake horsepower from a double stage pump with a 7 3/4. And a flow and a TDH. So again, this isn't, so it should be finding the flow. And then a TDH of 40 feet, okay? Is that what that says?
Yep.
Okay, and then 7 3/4 impeller and a double stage pump. Now here's how this is gonna work. See, a multi-stage pump are like pumps in series. The flow doesn't change, but the head does. What this pump curve does is it tells you what each stage individually does. Okay, that's what the pump curve does. So if you're looking at 40 feet for 2 stages, you got to divide that by 2. 20 feet per stage. And that's what this pump curve is set up for. to tell you what one bowl will do, one volute, one stage, whatever you want to call it, okay? So 40 over 2 gets you 20 feet per stage. So you don't want to go in on 40, you want to go in on 20 is what you want to do. Because this pump curve is set up to tell you what one stage will do. So that's the deal. And so now you're just going to track 20 across. Now there's other adjustments you have to make because you have to realize this is for one stage. So you're looking for the 7 3/4, so you just track it across. Are we good with that? We got any questions on that? So you're going to read it over there where I've got it marked. So you just read down from there. Okay. Now there's one other little trick on this, or not a trick, but something you got to remember about it, or a couple of them. So I got about 500 gallons, 540 gallons per minute, which, you know, you might have got 550, and I don't know. It's not like, my eyes aren't perfect. I'm just like anybody doing the best I can. Okay, so whatever, you know. Now, how about the efficiency? What's that going to be?
I'm looking at that and thinking it's going to be 68.
Right, but then you got to adjust it, right?
Wow, what's the adjustment?
Yeah, and look at that thing up in the upper right-hand corner.
It's hitting this. Mine, it looks like it's actually hitting the 70% curve.
Oh, it does? Oh,
Very close.
okay, we'll call it 70 then. Okay, and so it is 68, right? Because we got to take 2 from that. Yeah, okay. So that's an epsilon there, it means efficiency. And then how about the brake horsepower? All right, now that's, yeah, so 4 horsepower, but that's, again, this is for one stage. So if we double up the stages, what's going to happen to the horsepower? Double it, yeah, we got to double it, see? Because we're creating twice the head that we're showing on this pump curve, so it's going to, you know, you can't get that for free. It's going to double up the horsepower too. Okay, so that'll be 8 horsepower total. Okay. All right. So that's how the pump curves work. Okay. And when you, whenever they install a lift station or pumps, you should get a full operating manual that has all the stuff about it, and you should be a pump curve in there. They'll tell you how that thing will operate. So, you know, that's good information about a pump and how it'll work. So we okay with that? Good. Okay. Okay. Last little bit there on page 154. I've got just a little bit of information about cavitation. You know, I've got a couple of videos posted on that, and again, that's a good one to just to remember. Basically, what's happening is you're getting what are called implosions in the volute. Okay, cavitating pumps, they don't perform well and they sound like they're pumping rocks, and you're getting these big implosions that can really tear up impellers particularly. Now, here's the thing that can cause this. First is simple, it's air leaks in the intake piping. So if you have a pump that's doing this, that's one thing you want to be looking for, okay? Is if you have any sort of fittings in there that aren't sealed properly, you can be pulling air, and that causes problems. Too high of a discharge head can cause a real transition from the volute to the discharge piping. So that's another thing that can cause cavitation. And then the last thing is too low of an NPSH. So what NPSH is equal to is 34 feet, basically. You know, plus or minus, depends on how your elevation and all that, but that's basically atmospheric head is what that is. That's what you start with. Now, then you take away the static lift, how high you're lifting the water. So that's one thing you can change if you're having cavitation. Now, it's easy for me to say you can change it, but you know, you got to do some piping and move a pump and all that. So that's not easy. I'm not saying that is, but that is something you do. The vapor pressure. Now that's basically caused by temperature, so there isn't really too much you can do about that. And then minus the head loss, and there is something you can do about that, because on your intake piping, you don't want a bunch of valves and stuff on that side. The valves should be upstream. That's the safer place to put them, because when you start putting fittings and valves on your intake piping, you increase the head loss. So if you have true cavitation, you know, you want to check these two and check those, but and the problem isn't in either of those. What you can do is move the pump down if you can. Again, may or may not be able to do that. Also, look at that intake piping and try and reduce the constrictions, fittings, that kind of stuff in it. Make a nice, clean, open path to get the water up to the pump. Okay, that'll reduce cavitation. All right.
Yeah, in somewhere they have a slight reducer before the actual pump itself.
Yeah, and that's trying to get that head loss down. Now, the one thing on those reducers, though, you know, so we're just talking about the intake piping can be oversized, and then you have to put a little bit of a reducer in there. There's actually a special type of reducer that's made called an eccentric reducer. You don't want a reducer, one of these kind, where it kind of does this and then next down, because you get air bubbles up in there. Because when the dissolved oxygen comes out of the water, which it will, it'll rise, it'll collect in that little cavity there, and that's trouble. So they actually make a reducer for this, for pumps. It's an eccentric, meaning it's not centered. It reduces like this, okay? So it just bends up from the bottom up, so you don't end up with a pocket in there that'll collect air. So this is the type of reducer to use on the intake piping before you hit the pump, because you just don't collect air. Okay. All right. So all right. So I'll try and get this homework back to you tomorrow. Okay. I'll work on that and get that back to you. Friday, I don't know if. I'll just try and review for the test a bit, I guess, on Friday. If you have questions, you know, you could come and ask me, or you could email me if you have questions or whatever. I mean, you know, I know a lot of you aren't here on Fridays, but so, you know, I'll just go over the basic stuff and what we're going to do there. Okay. Okay, one last little bit on cavitation, because that's good practical information. If I can get there. So we'll do a little applied cavitation pop quiz. If your pump is, which one of these pump setups that I'm showing you right now would tend to cavitate more, the one on the top or the one on the bottom?
Probably the one on the top.
Yeah, why is the one on the bottom the one that's going to cavitate? Yeah, you're lifting water. See here, I'm not too worried about cavitation with this setup because the intake reservoir is above the pump. So gravity is pushing water in there. I'm not too worried about not having enough energy in that water when it hits that pump. This is also the setup for the submersible, you know. They don't cavitate, I don't think. You know, I wouldn't be concerned about that. This is where I'm worried about it, because you're lifting water up out of that reservoir, and that's going to cut down on your NPSH. Okay. All right. So we good to go? All right.